Hello and welcome. This video is going to be talking about matter, which is talked about in Chapter 3, Sections 1 through 7 in our TRO textbook. As we saw in our Chapter 1, when we're talking about the chemical world, our definitions of chemistry all involve substances, which are matter. So in this video, we're going to be talking specifically about matter and just different ways to look at it, classify it, what it is, all of those types of things. Our purpose, our goals by the end of this chapter or this video is to be able to define and describe matter. What is it? What does it look like? What am I talking about? And then we're also going to look at how to describe different ways to classify it, different properties associated with the states of matter, such as solid, liquid, gas, how to classify matter based on composition or physical state, how to identify phase changes, how to distinguish between chemical and physical properties and or changes, how to interpret and identify key features of a chemical equation to show those different changes, and then lastly we will look at our most common law we'll interact with this semester, which is the law of conservation of mass and how it applies to chemical reactions. So to start out, when we talk about matter, matter is technically defined as anything that occupies space and has mass. As long as it has these two things, it doesn't matter how big it is or how small it is, as long as it occupies space and has mass, it classifies itself as matter. So this could be something as small as dust or germs. It could be something as big and powerful as water. It could be plastics that we see in our everyday lives, or it could be something like air, which is a gas that's all around us. Some examples that aren't matter are things like energy or thoughts. Those things don't have these same qualifications of having mass, so they don't necessarily qualify as matter. All matter is made up of some fundamental building blocks, which are called atoms. We'll go deeper into what atoms are on the next slide, but essentially all matter is made up of these atoms. Once we have matter and identify it, we can then start classifying it to better understand it. So that would be classifying based on composition. So what is the matter made of? You can also look at physical state. So what form is it in? Is it a solid? Is it a liquid or a gas? It can have different properties. So different types of matter have different properties, and they also undergo different types of changes. They can react with certain things in certain situations. So like I said, all matter is made up of atoms. So atoms were actually first theorized in 5th century BC by some Greek philosophers. Essentially what their theory said was that at some point, if I try to break down matter, eventually I'm going to hit some point where I can't break it down any further. So those are indivisible particles, and they called those atomos, which means indivisible. For example, if I have a piece of wood or a block of wood, like a log of wood, and I start chopping at it, chop it down, chop it down, chop it down. I keep chopping it down, even to the point where I can't see it with my naked eye. Eventually, I'm going to hit some point where I can't break it down anymore. So then this theory expanded to the idea that there are atoms, there are fundamental building blocks. And this is an understood concept now. It's not necessarily a theory anymore. But we do believe that all matter is composed of these small indivisible particles called atoms. So they can't be divided anymore. If I have atoms, there are different types of atoms that can make up different things. So there are different versions of these atoms. Now, each version of an atom of a same type is called an element. So if I have several atoms that contain the same, or that are the same, for example, a bunch of carbon atoms, then that element would be called carbon or oxygen or whatever. But essentially what that is one type of atom. In order to organize all of these different types of atoms, we use something called the periodic table of elements. So this is why it's super important to chemists, because if we're studying matter, all matter is made up of elements. There are tons of different types of elements. We need this piece of paper in order to understand what's going on. So in our course, I do have the periodic table for you to print, as well as links to other periodic tables. And then I have this one here for you to take a look at. If you look at it, it's organized in a certain fashion, which we'll learn about later in the semester. Mine is nice and colorful. Again, you'll learn what these different colored regions are. But I just wanted to show you this since we use this all the time. This is kind of an important piece to our class. So where do you want to start right away? So each box represents a different element, and that element has some special things about it. So one of those things is going to be its chemical symbol. The chemical symbol always has at least one letter in it. That first letter will always be capitalized. The second letter will be always lowercase, as in this example. And then each element also has a name. So Fe stands for iron. So if I have this compound or this element, I'm talking about iron. There also is something called an atomic number or a whole number in the top of each box here. That's another way to signify a specific element. If you look at the organization, it goes in increasing number 1, 2, 3, 4, 5. So it increases as you go across and increases as you go down. And that's just how we keep track of our different types of elements. So right now, what you want to start with is actually knowing the name and symbol combination. So if you see the Fe, do you know that's iron? For the name iron, if you see this in a compound, do you know that Fe is there? Or if you see this written, do you know Fe means iron? There are 118 elements, so where do you start? What's kind of the starting point? So I know it can be a little overwhelming thinking, oh, I have to know all 118. Eventually we will use most of the elements, but for now what you want to focus on is knowing the name symbol combinations. And I highlighted kind of the ones you're going to use the most, so I figure that's probably the best place to start for now. So study these ones that are highlighted to start out to kind of give you a good jumping off place, and then you can obviously start expanding to more elements there. The faster you learn these, the easier it's going to be to start naming or writing out compounds, those types of things. The other thing you want to start practicing is locating them. So if I say, hey, I need some information about magnesium, you have to know where to look for it, because otherwise you're going to be scrolling down each column and it's just going to take forever. So if you know that name symbol combination or where it's located, it's going to make your life a little easier in the long run. In most cases, the symbols are going to be the same as the name. For example, magnesium has Mg sounds in it, so you have Mg. It might be a little tricky because there is also manganese, which is Mn, so just knowing those combinations. But things like krypton over here, Kr, that's pretty straightforward. Chlorine, Cl. There are some that aren't named associated with things that we would think are normal, like sodium and potassium are Na and K. Silver and gold, Ag and Au. This just comes from what native language were they actually formed in, and we've just carried those symbols over, even if we've changed the common name we use in English. So just be mindful of these different symbol combinations for the names, but just get some practice whether you want to make flashcards or like print a blank periodic table and start filling it with symbols. Whatever you want to do to start learning these different name symbol combinations and start locating them on the periodic table. One of the things we'll be using these elements for, or different atoms for, are actually creating compounds and molecules. So now we're actually going to be starting to put things together to make a compound. So you have individual elements that then come together, and they are chemically bonded in characteristic proportions. So when things are chemically bonded, that means, for example, if I have hydrochloric acid, which is HCl, hydrochloric acid is chemically bonded, so there's something holding the hydrogen and chlorine together. They're bonded, they're held together, they're glued together, they're stuck together. It requires a lot of energy to actually break that bond, so this is some type of substance or a form of matter. How it's bonded together is in characteristic proportions, so no matter where I go, what day I go, and what time of day I go, where in the world I go, if I talk about hydrochloric acid, it's always in this ratio of 1 hydrogen to 1 chlorine, so HCl. What I wrote up here is actually called a chemical formula, showing you, using the symbols, what is being chemically bonded together. Notice I added these little numbers down below. Those are subscripts implying how many of each element is present in that compound. I have another example here for you with water. So we usually call water water. That's its common name. We also have a systematic name. This is agreed upon naming system from chemists. We will learn how to use this for lots of different compounds. The systematic name for water is dihydrogen monoxide. So notice water in the chemical formula has two H's and one O. So then hydrogen is the name for H and oxygen is the name for O. So that's where I'm getting the oxide and the hydrogen. From the chemical formula, I have two H's and one O, and it just so happens that those are in this name. Not all compounds are named this simply, but this would be how you would represent water. You can also draw water in a bunch of different ways. So you have the Lewis dot structure, a bonding model, a ball and stick model, and a space filling model. These three at the end are just pictures. I wanted to show you what a molecule could look like if you see pictures in a book or online. So you know what these drawings are actually representing. They're representing the different elements and how they're bonded. This first one here, the Lewis dot structure, towards the end of the semester we will actually learn how this is drawn, but these lines that I have drawn here are actually showing how the bonds are being formed in a water molecule, so you have that chemical bond. Now that we know how to make up matter, we can start classifying it based off of what it's actually made of. So there's two ways you can classify based on composition. So you can classify something as a pure substance or a mixture. A pure substance is exactly what it sounds like. It's pure, it's by itself in essence, it's just one type of substance. The difference is then a mixture. A mixture involves multiple types of substances. So pure substances are elements or your fundamental building blocks that you find on the periodic table, for example, chlorine by itself. Then a compound is elements that are chemically bonded together to form one type of substance. For example, if I have sodium and I have chlorine coming together, sodium chloride, sodium and chlorine are chemically bonded based on this chemical formula, but it's only one type of compound. So these would be pure. An element by itself is purely an element, pure substance. And then if I have a compound like chemically bonded together like sodium chloride, that would be a pure substance. In this drawing, notice I have an element, only one type of element is present there. Maybe this is something like Na. And then I have a compound, this one specifically is carbon dioxide or CO2. So here I have carbon in the middle and then two oxygens on either side. So these are all examples of pure substances because they're isolated by themselves. A solution or a mixture, on the other hand, I have homogeneous or homogeneous mixtures or heterogeneous. These are combinations of things. So this could be, what if I had NaCl in water? Or what if I had CO2 and Na in a beaker? This would be a mixture, and this would be a mixture. Notice I have the plus sign. I have more than one type of thing there, or more than one type of substance. How it's mixed is what determines if it's homogeneous or heterogeneous. So homogeneous or homogeneous is an even distribution of the combination of them. So if I have 3 substances, 6 substances, it just means that there's some order, it's evenly distributed, like I have shown in this picture. Purple sphere, teal sphere, purple sphere, teal sphere. Say that 10 times fast. Then I have my heterogeneous mixture, which is different. Notice how I have all of the purple spheres on one side and the teal spheres in a different. So this is heterogeneous, meaning I don't have an even distribution. So that combination or that distribution is not even. So pure substance is one type of thing, one type of substance, and then a mixture is a several types of substances mixed together. So to make sure you're following along, I've included a few checkpoints. So what I recommend is you try to think of the answer before I give it to you. If you need to pause the video to make sure you're understanding before I give you the answer, that's fine. Or if you want to put these in your notes so that way you can keep track or have some reference. So for these 4 different substances, what's the best way to classify them based on composition? So if I have chocolate chip ice cream, is that best classified as an element, a compound, a homogeneous mixture, or a heterogeneous mixture? So the first thing I would do is say, okay, well, I know it's a mixture because I know it has several different things in it. It has cream, it has chocolate chips, it has sugar, it has all of these different ingredients in it. So it is a mixture, it's not just one type of thing. How is it mixed? Is it evenly mixed or unevenly mixed? Well, if I have those chocolate chips, it's usually unevenly mixed, so it would be heterogeneous. If you think about a scoop of ice cream, does every single person always get the same exact amount and size of chocolate chips? And the answer is no. So that would be a heterogeneous mixture. What about wine? Again, you would think, what is it made of? This is also a mixture. It has lots of different things in it. However, different this time. Every time I take a sip of wine or pour a glass of wine, it has the exact same ingredients and the exact same consistency, exact same amount, everything. That would be a homogeneous mixture or a homogeneous mixture. Next, I have sodium chloride, which is table salt. So sodium and chloride, remember these are each elements NaCl, and it's table salt. This is a pure substance because it's not mixed with anything, but it would be a compound because I have these chemically bonded to each other to make sodium chloride, to make the table salt. So table salt is not mixed with anything, it's just a pure substance. And then because it's a combination of more than one element, it would be a compound. And then gold is best classified again as a pure substance if I have a pure piece of gold. And then because gold is one element found on the periodic table, it is classified best as an element. So that's how you can classify the type of composition you have based on what matter you have. You can also classify your matter based on its physical state. So how does it appear physically and how are the atoms or molecules arranged within that substance? So we have three physical states, solid, liquid, and gas. If you've been keeping up on current literature or have ever had any experience, you might say, well, there are more than these physical states, but we are only focusing on these physical states in chemistry. So when you classify something as a solid, basically what you're implying here is the arrangement of atoms are in a certain way, just like if you classify as a liquid or a gas, and they have certain behaviors associated with them. So if I classify something as a solid, essentially what I'm saying here is that atoms or molecules are closely packed to each other in fixed locations. They can vibrate and oscillate, but they don't move around each other, which gives rise to the fixed shape and volume. This is an analogy here would be something like students sitting in assigned seats in a classroom during a class. Let's say students are sitting in their assigned seats, they're stuck in their seats, they can't get up from their seats and move around, but they're sitting in those seats. However, they can write with their pen, they can raise their hand, they can dig in their bag, they can shake their leg, whatever they're doing in their seats, they're moving in their seats, but they're not moving out of their seats. And then that would mean my classroom arrangement would have a specific volume and shape because my students are stuck in their seats. If I were to classify something as a liquid, it's very similar to a solid, except for now the students are allowed to get up out of their seats. So the atoms and molecules are still close to each other, but they're free to move around. So this would be like if I asked you guys to get up and start mingling with each other in this classroom and you guys can go around and meet each other. You're still confined to this tight space, so you're very close to each other, but you have this freedom to move around now. So you still have a fixed volume, and now the container has its own, the liquid now can take the shape of a container. So if you've ever watched those YouTube videos of people trying to trick kids to pick the different volumes when it's really less liquid than the other shape, that's basically a property of a liquid. A gas is then very similar to a liquid, except for now atoms and molecules are widely separated and free to move about each other. So this would be if I said, go to the football field, a football field somewhere, and just 20 people go to the football field and move around. You have to stay in the football field, but you can go anywhere in there. So if you imagine 20 people on a football field, they can get pretty far apart, but they're free to move anywhere in that space. So you would take the shape of your container, take the volume up of that container, and then those people can be expanded or expressed, or expanded or compressed, depending on what you want to do with that gas. So those are some properties of solids, liquids, and gases. Since they're very similar, you can actually convert via a phase change. So what phase it is, it's a solid phase, well, I can change it into a liquid phase, or if I have a gas phase, I could change it back down. So this all depends on energy and how much energy is absorbed or released. Usually we call that heat in order to do these phase changes, but you can cause some substance to go through these different phase changes. Again, I chose water because I figure most people have some experience with water, ice, vapor, that kind of stuff, steam. But this applies to any substance that could potentially go through the different phases. These numbers here that say cal, that's how much energy is required to do this. For water specifically, each substance is going to have a different number there. I just wanted to kind of show you different things that are going on. So if I have a solid, it can become a liquid. If I have a liquid, it can become a gas. And these changes have specific names. So if a solid goes to a liquid, it's melted. If the liquid then goes to a gas, it's evaporated, or it undergoes evaporation. These two have other terms that are commonly used. Melting is also called fusion, and then evaporation is also referred to as vaporization. So those also have other terms. If you go directly from a solid to a gas without seeing any presence of a liquid, you actually undergo sublimation. So all of the red lines here are going to a higher energy state, or getting less and less ordered, increasing the disorder. So solid is in that confinement, liquid is a little more disordered, gas is just wild around. You can also go back the other way. So if I go from a gas to a liquid, I have condensation. If I go from a liquid to a solid, I have freezing. And then the opposite of sublimation is deposition. Melting, evaporation, freezing, and condensation are all commonly seen in our daily lives. Deposition and sublimation aren't seen as often just because they require such huge energy changes. Just a lot of energy is required to make these happen. The biggest example I have for sublimation is if you've ever seen dry ice. Usually at a Halloween party, you put it in your drinks, and then it starts to make that smoke or make that spooky appearance, but it keeps your drinks cold. So it's because it's actually, but not watery, it's because it's going from a solid to a gas. It's doing this phase change. So again, let's practice to see if we understand the concepts of our physical states or our phases. Again, if you want to pause to see if you got all the answers without me telling you what they are, first pause the video, write them down, see if you got them correct. So if I have a substance that takes the shape of the container and is incompressible, that best represents a liquid. A liquid can take the shape of its container but cannot be compressed because they're already close together. If I have a substance that takes the shape of a container and is compressible this time, this best represents a gas. Because a gas is widely spaced, it can be compressed or expanded. Molecules that are in fixed locations and closely packed but can vibrate in place best represents a solid, because you have your atoms in specific positions, but they can't get out of those positions, but they can vibrate in them. And then molecules that are free to move about but are still closely packed best describes the molecules in a liquid. Because they are closely packed but they're free to move about, this best represents liquid. So now that I know what matter is, what it's composed of, how to classify it, and what physical states it can undergo, now we can talk about other properties. So some properties we can talk about are physical and chemical. These describe characteristics that distinguish properties or distinguish substances from one another. So the purpose of classifying molecules or doing this is to kind of make sense, look for patterns, figure out what's going on. So there's a difference between physical and chemical based on what is actually happening or what type of property I'm trying to explain about that substance. So if I'm just describing what the material is like, what the substance is like, without actually changing the substance into something else, it's actually considered a physical property. So this could be things like color. It's just sitting on my bench top and it looks like a white powder. That would be a physical property. Other physical properties are like density. When I place the object, does it sink or float? That is a physical inherent property. If I have something like melting point, that helps me identify when that phase changes from a solid to a liquid, so it melts. Malleability, if you haven't heard of this word before, it just means how if it can be reformed like clay or a wire or metal, I can heat it up and reform it. Or is it very brittle? It just snaps in half. And then solubility is another one. Solubility is talking about dissolving. So does it dissolve in solution or in some substance to make some type of mixture? Like salt and sugar can both be dissolved in water. That is a physical property of your sugar or salt. So physical properties are usually looking at what is that substance like, what is it appearing like, what is that normal behavior. Usually your physical properties can be used to identify substances because that's just the inherent nature, that's just what that substance is like. Whereas a chemical property is actually used by or is measured by changing this actual substance. So even if I have the same elements present, if they're bonded in a different way or bonded with different elements before and after some type of process, that essentially means that it's undergone some type of chemical or it's just a chemical property. So something easily starts on fire, that's flammability. That's a property of that substance. It easily catches on fire. If it reacts in certain situations, if it's toxic or acidic, all of those different things are chemical properties because some type of chemical substance change is happening when it undergoes these processes. Which leads us to the idea that things can also be classified as physical and chemical changes. So if I make a change to that substance, but it's not actually changing the chemical composition, I still have the same compound or molecule or atom in the exact same arrangement before and after I make that change, that would be a physical change. So you have a change in appearance, but not a change in what chemical you have in what type of bond. So this could be something like your phase changes. If I go from a solid to a gas, but I have the same substance, that would be an example of a physical change. So would be like cutting, smashing, breaking, or grinding things up. Essentially, I have the same substance. It's just looking a little different. If I have a chemical change, however, this means that I'm actually changing the chemical composition. So like I said, I may have the same elements, but they're bonded to different things and they're bonded in different ways. This can also be associated with a change in appearance, but the main thing you're looking for is a new or different substance. Things are now bonded in a different way. Maybe I had just hydrogen before and now I have H2O or something like that. Again, let's do a checkpoint to make sure that we're understanding. So again, if you want to pause to see if you can make sure you have these down. Or before I give you the answer. So if I have the flammability of alcohol, the fact that alcohol starts on fire is a physical or a chemical property of alcohol because I'm changing it chemically. If I have the color of a gold ring, this is just talking about its color, its inherent physical appearance. This is a physical property of a gold ring. If I have water boiling on the stove, water is going from a liquid form to a gaseous form. So this, I'm not actually changing the fact that I have water, I'm just changing how it looks. So that would be my physical change. And then lastly, if the process of the Statue of Liberty turning green over time, well, what's causing that process? It's a chemical reaction or some type of chemical change that's happening. So the flammability of alcohol is a chemical property. The color of a gold ring is a physical property. The water boiling on the stove is a physical change. And then the process of the Statue of Liberty turning green over time is a chemical change. In order to represent all of these changes in matter, the thing we use is called a chemical equation. So if you've taken chemistry before, you've seen these. These are our chemical reactions or chemical equations. So if you want to pause to take a second to kind of look at these to see what they look like, look for some similarities or even differences. I'm going to point out some of those similarities now. So down the center, you have these arrows on every single equation. Those arrows are what is representing the fact that there has been a change. You have a before and an after. So the left side is the before, the right side is the after. The left side we typically call the reactants or reagents. Those are your starting chemicals, what you're starting with. The right-hand side is always your products or what is produced. So the left-hand side is what you're mixing together. The right-hand side is what is formed as a result of that mixing. Notice on each side you have your chemical compounds. So these have your different symbols. Notice you have different combinations of subscripts and letters and all that stuff. We'll get into those later on in the semester. But just for now, looking at all of these, you have different compounds. So what they're separated by, how I know they're different compounds, is because they're separated by a plus sign. So anytime you see a plus sign, that means they're not chemically bonded, but they're mixed. Whereas if there's no plus sign, that means they're a chemical compound and they are chemically bonded to each other. Following each compound, you'll see these parentheses with letters in them. These are indicating what physical state they're actually present in. So S stands for the solid, so that's implying the rigid atom arrangement. Liquid, gas, they're implying those properties we talked about. There is one we didn't talk about, which is aqueous. Essentially, the purpose of aqueous, some people call it aqueous, essentially just means that that substance is actually a homogeneous mixture or a solution, and it's actually dissolved in water. So if I have MgSO3, that means this is not a pure substance, but it's actually dissolved in water because the AQ is coming after it. And then out in front, you have these things called balancing coefficients. Essentially, this is so we don't violate one of our major laws. We'll talk about that law on the next slide, which is the law of conservation of mass. Essentially, what that says is you can't have stuff just disappear throughout a reaction. If you start with 2 hydrogens, you have to end with 2 hydrogens. Even if it's bonded to something differently, the same number of atoms must exist. So you have to have those balancing coefficients in order to account for the correct number of atoms. So just to kind of look at these now, take a second to think to yourself, of these 3 chemical equations, which ones represent physical changes and which ones represent chemical changes? So for this first one, if you said that this represents a chemical change, you would be correct. How I know that is because I have hydrogen by itself here, or H2, then I have a plus sign, and then I have oxygen. Here I don't have a plus sign, so what that means is that I'm adding hydrogen and oxygen to create water. So I have 2 substances on this side, I have 1 substance on this side. So yes, I have the same elements, but how they're chemically bonded has changed, so that means I have a change in chemical composition, so this should be a chemical change. For the second reaction, if you said physical, you would be correct. This is an example of a physical change because I have the same compound beginning and end, but my physical state has changed. So I went from a solid to a gas, so this is an example of sublimation. For the third reaction, if you said chemical, again, you would be correct. This is because I have elements on the left and right that are bonded in a certain arrangement that's not the same. If I focus specifically on what Mg is bonded to in the beginning and end, I would say in the beginning, magnesium was bonded with sulfur and oxygen. In the product side, my magnesium is bonded with oxygen and hydrogen. That means I have a different chemical bond here, and I have a different type of bonding, different behavior, different compounds, so I would have a chemical change. I also can check my physical states. I do have a change in my physical states as well, which is fine. Like we said, sometimes you will see both a physical change and a physical change in appearance along with a chemical change. So this would be an example of a chemical reaction or a chemical change. So let's talk about our last law, or our last thing here, which is the law of conservation of mass. This is where those balancing coefficients come from. Basically, like I said, this means matter is neither created nor destroyed through a chemical reaction, but it can change forms. So this means that elements can change who they're bonded to throughout a reaction, but the amount of elements should not change. So if you added up all the masses before the chemical reaction, and you added up all the masses after the chemical reaction, if you perform the reaction in a closed system, then you should get the same masses beginning and end. You can also call this law of conservation of matter. It just means matter is neither created nor destroyed. It can change form. So closed system just means you have some type of closed container, so your matter just can't fall out somewhere. If you weigh the entire beaker with these solutions before you mix them, you get a certain mass. You shake up the flask, you get the same mass at the end. Even if now calcium is paired with sulfate instead of being paired with chlorine in the beginning. So yes, my pairs change, but I have the same number and type of atoms from beginning to end. So that will be your law of conservation of mass. This allows us to do lots of calculations and relationships mathematically because matter is neither created nor destroyed, and it has to be accounted for. So this concludes our discussion on matter for Chapter 3, Sections 1 through 7 of the Trow book. I hope you have a firm understanding of what matter is, how to classify it, what different composition it can undertake, what the meaning of the different physical states are, a basic introduction to our chemical reactions and the law of conservation of mass.